As of now, in thermodynamics, we are already only discussing about closed system. Closed system means when there is no mass transfer, only energy transfer will take place. So we will see, we already studied what is the work transfer in various process under a closed system, what are the heat transfer, what is the first law of thermodynamics for a closed system, right? Now we move on to our open system. We already know that what is the meaning of open system. In open system, there is both mass transfer as well as your heat transfer or energy transfer, right? Mass is also transferred from the system. Either mass is coming in the system or mass can go out of the system, and also energy can enter the system or leave the system. So we are discussing now open system. So the first topic will be our flow work. So let us see what is the meaning of flow work. Flow work is that work transfer which is involved in moving a fluid particle for either it will enter the system or it will leave the system. Suppose this is a container. From here this fluid is coming in the system, and from here this gas will go out. And with the help of this red line, I have to demarcate the boundary. This red line, red dotted line is our boundary. We know that we have to show the boundary that this is our system. Other than this system, everything is surrounding. So this is your control volume, right? Our discussion will be confined to this space only. Air is entering from this inlet valve and air is coming out from this outlet valve, right? So the flow work is the work transfer involved in causing this fluid element either to enter the control volume or to leave the control volume, right? What is the work required for this air to come into the control volume or to go out of this control volume is known as your flow work. Now let us suppose we'll see how or why this flow work is needed. Suppose this is our inlet point. I mark it as your I. Suppose I is for inlet and O is for outlet, right? Just as a nomenclature we are using I and O. Now I am considering three layers. So understand, now I am considering three particles. Suppose here this is a one layer of fluid which is coming inside the system. Ahead of this layer there is one other layer. This layer is adjacent to the blue one, adjacent to this, and behind this layer there is another layer, right? These three layers we show, right? First layer is of this black layer, this blue one and this red one. Now if I am only considering that this blue layer has to enter this, or you can say this blue layer has to enter this control volume, right? This blue layer has to enter this control volume. Here some particle is there, some fluid particle is there. It has to enter in this control volume. Now to enter this control volume, for this blue layer to enter this control volume, it has to push this red layer, right? It has to push this red layer. After, when this red layer will enter into the system, then only this blue layer can enter into the system. So it has to push this red layer inside the system. So, or you can say, or you can understand like this: if this red layer has to enter into the system, there is a particle here on this red section. It has to enter into the system. It needs some work, right? It needs some work for this movement, right? So the work required for this layer to enter into the system is given by the layer which is adjacent to it. So this blue layer will push this red layer, or you can say this blue layer will give some work, some of its internal work. See, there is nothing happened from the outside. We are not giving any work here, right? So this layer, suppose this layer, this blue layer has some energy, suppose say 100 units. From this 100 units, it spare, suppose say 20 units to this red layer and push it with 20 units so that it can enter into this system, right? So the layers, this layer will give the work of 20 units to this red layer so that it can enter into the system. So this amount of work which we required to maintain the flow, right? To maintain the flow, so like that, this black layer will have to give 20 units to this blue layer so that it can enter into the system. So this work which is helping this fluid particle to flow into the system or to go out of the system, here also the things are like that. Here also some 3 layers are there, fluid layers are there. If this fluid layer has to go out of the system, something inside this has to push it outside, right? So this work which is help in maintaining the flow is known as your flow work. So in case of your open system only, the flow work will exist. If I say the flow work for a case of closed system will be 0, because in closed system there is no mass transfer, there is no mass flow. So the flow work will only holds good in your open system, and it is that work which is required to maintain this flow, either to enter into the system or to go out of the system, right? So the flow work will be equal to your pressure into specific volume. Flow work will be equal to pressure at this point into specific volume. If I write this is inlet, so I write Pi into Vi, right? This is specific volume. This V, this nu is equal to volume per unit mass, right? We already studied what is the specific properties. Specific properties are properties per unit mass. So this nu is, or small v is equal to volume per unit mass, right? So this is Pi into Vi. This is the work at the inlet. Now this work is done on the system, right? This layer will, this black one will push this blue one or this red one to enter into the system. So this is the work done on the system. So if the work is done on the system, then the work will be negative. As per our sign convention, work done by the system positive, work done on the system negative. So here also system is doing some work on this layer to push it out of the system, right? It has to push this layer out of the system. So this your system will do some work on this layer. So it is work done by the system. If work is done by the system, then that work will be positive and the value will be P naught, naught is for outlet, into specific volume at outlet, right? So this is the flow work, and we can write that simply flow work is equal to pressure into specific volume, right? Pressure into specific volume. So the flow work is only exist in your open system, right? Now let us move towards your steady flow energy equation, right? We already studied closed system and the first law of thermodynamics for a closed system. Now we want to know what is the first law of thermodynamics for a open system, right? System may be open, may be closed. So we are heading towards the first law of thermodynamics for an open system. Before that, we'll see what is the steady flow energy equation. In this, the name suggests the flow is steady. The flow is steady. If the flow is steady, what will be its energy equation, right? So first of all, let us see what is the meaning of steady flow. We already studied two types of flow, steady flow and uniform flow. Just for a recall, we'll explain it further. Steady flow means a flow is said to be a steady flow if the properties do not vary with respect to time. Pressure, volume, temperature will not vary with respect to time at any given section. This is the most important thing, at any given section, right? If the properties are not changing with respect to time at a particular section, right? If you are varying the time, if I am saying, if my study is there like at t is equal to 1 second, I just notice some properties like pressure, temperature for some time. So with respect to time, if the properties are not changing at one section, then the flow is said to be a steady flow. For example, suppose this is a pipe, right? This is a pipeline, and in this direction fluid is coming in and fluid goes out. So this is the flow, right? Some water is flowing in this direction. I take three sections in this pipe. Three sections, this is section 1, this is section 2, this is section 3, right? These are the three sections which I am taking, and I am saying, let us say when the time is 1 second, right? After this flow, after 1 second, I want to know what is the velocity of this water at different points. In all these 3 points, what will be the velocity of water? Suppose velocity is also a property. What will be the velocity of water, or what will be the pressure of water at these 3 points when time is equal to 1 second? So I am saying, let us say that velocity at this point 1 is suppose 2 meter per second, velocity at this point 2 is suppose 3 meter per second, and velocity at point 3 is suppose 5 meter per second, right? I am just taking a random values. Suppose when t is equal to 1 second, velocity here is 2, velocity at this point is 3, and velocity at this point is 5. Now the time is going on. So I am saying, okay, after 10 second, if I see this pipe, after 10 second, time changes. So if after 10 second, velocity at one point, that is, if I am saying velocity at this given section is not changing, the velocity is same, that is 2 meter per second, velocity at this point is same, that is 3 meter per second, and velocity at this point, third point, is same, which is equal to 5 meter per second. So we can say that at one section in different times, your properties are not changing, then this flow is a steady flow. At different sections, property may vary, right? At different sections, your properties will vary, velocity is different, 2, 3, 5, but when the time changes at one section, if property is not changing, then this is your steady flow. So this is the meaning of your steady flow. Properties will not change with respect to time at any given section. Section must be fixed, right? So we want to know what is the steady flow energy equation in case of an open system, right? Suppose this is your open system where your fluid is coming in, fluid is going out. We want to know what is the steady flow energy equation for this. If there is a steady flow in this, that means nothing can change with respect to time in this control volume. This is my system. If I am saying this is my steady flow equation, steady flow is there. Steady flow means there shall not be any change in this control volume with respect to time. What can change in this? Suppose mass is coming, mass goes out, so mass can change. Suppose 3 particles enter, only 2 particles left, 1 particle is still inside this system, the system or control volume mass will change, right? So if the flow is steady, so the first condition for a steady flow is there should not be any accumulation of mass in the control volume. In the control volume, there should not be any change of mass, right? When it will happen? It will happen only when the mass which is coming in is equal to the mass which goes out, right? So that the net change of the control volume mass will be 0. So that there should not be any accumulation of mass in the control volume. So we can say that the rate of change of mass with respect to time, steady flow is there, so time is changing. So with respect to time, if the mass of control volume is not changing, that means the change of mass with respect to time is 0. Or for a control volume, we can say that this is the first condition for a steady flow. Steady flow means there should not be any change on this control volume. In open system, only two things can be possible. Either mass can transfer or energy can transfer, or both. So there are two possibilities in an open system. First one, mass can change in control volume. Second one, energy can change, right? So if both of them are not changing in the control volume, so we can say that our flow is a steady flow. So the steady flow means, first condition is there should not be any change of mass in control volume with respect to time, which means the mass flow rate m dot, if we are writing anything like m dot, this dot means your rate with respect to time. So the mass flow rate which comes inside the system must be equal to mass flow rate which goes out of the system, so that the net mass of the control volume will not change. This is the first equation. Second equation would be, there should not be any change of energy of control volume. No energy can change, right? What is the energy? Suppose in this control volume, heat is coming inside the system, or heat can go out of the system, or system is doing some work on the surrounding, or surrounding is doing some work on the system. So there are number of possibilities are there. We are saying that if the flow is steady, then there should not be any change in the energy of control volume. Means energy which can be work or which can be heat, energy which is coming inside the system will be equal to energy which can go out of the system, right? So there should not be any change of energy. dE by dt for a control volume is equal to 0 for a steady flow. That means energy rate which comes in will be equal to rate of energy which goes out. We are talking about rate because in an open system this flow is continuous, right? Flow is continuous. In open system, if a air is trapped in a system, in a closed system, it cannot change, right? There is no mass transfer in it. But in case of an open system, this is a continuous process with respect to time. So we are dealing with the rate with respect to time we are talking about. Now, so these are the two equations for the steady flow. First one is there should not be any change of mass in control volume. Second one is there should not be any change of energy in the control volume, right? Now we want to, our topic will be steady flow energy equation. Suppose I am again drawing this. This is the control volume. We have this system. This is the inlet. As we know, this is inlet and this is outlet. Fluid is flowing in this direction into the system. Fluid will go out from this point. Suppose we are taking heat is added to the system, which is Q. Q is heat added to the system, and this control volume is doing some work on the surrounding. That is, work is done by the system on the surrounding. That is WCV. This is control volume work, right? Control volume is, or the system is doing some work on the surrounding. So we want to know what is the energy at this point 1. What is the energy at this point 1? When a fluid is flowing, just remember, when a fluid is flowing in this direction, what are the different energies it is having? It is having some temperature. Because of that temperature, there is an internal energy, right? U1. U1 is an internal energy because of temperature. It has some temperature. Suppose T1 corresponds to the T1. It has some internal energy U1. Flow work is required, as we know, because of this pressure or because of this flow. Some flow work is required to enter into the system. So it must have that flow work in it, right? This flow work will come from the fluid itself, right? We are not doing anything to flow this. This flow work will come from the particle, from the fluid itself. So it must have this flow work. This fluid will enter into the system with some velocity, right? With some velocity, some speed must be there. Let us say V1 is the velocity at inlet. V1 is the velocity at inlet. In thermodynamics, V is for volume. I am just writing, and if I write this V dash, this is for velocity, because the same nomenclature is there. Same, we are using same letters. So we are using V for volume and V star or V dash is for velocity, right? So that there should not be any confusion. Okay, so it is moving with some velocity v. So suppose v1 is the velocity at inlet, v1 square upon 2 energy. We are writing energy, velocity is kinetic energy is half mv square, and we are writing all these terms in a specific. This is your specific internal energy, that is internal energy per unit mass. This is the flow work per unit mass, P1 into V1. This is specific volume. Kinetic energy is half mv square, and if I divided it by m per unit mass, so m will cancel out. So 1 by 2 v square by v square is kinetic energy per unit mass. So this is because of velocity v1. It is having some height. This must be at some height. Suppose there is some datum, some reference is there. Because of some height, the fluid will have some potential energy. What is the value of potential energy? Is mg into height z per unit mass, so will be equal to g into z. So suppose the height of this inlet valve is 1 z1, so g z1. This is the energy at which is coming inside the system, and also we are adding some heat to the system, so this is the Q. So this much amount of energy is adding to the system, right? This much of energy is coming inside the system because of temperature U1, flow work, because of velocity some kinetic energy, because of some height potential energy, and from surrounding you are adding some heat to the system, so that heat. This is the total energy which is coming inside the system, right? This is the total energy which is coming inside the system. Now we want to know what is the total energy which goes out of the system. So when the fluid is coming out of this system, suppose its temperature is T2, with respect to T2 some internal energy U2, this is per unit mass. Specific some flow work P2 V2, it goes out with some other velocity, say V2. With respect to V2 some kinetic energy must be there, that is V2 square by 2, plus because of some height Z2 it is potential energy GZ2. This is the total energy which is going out of the system, and also this system, this control volume is doing some work on the surrounding also, that is WCV, so plus WCV. This much of energy is going out of the system, and this much of energy is coming inside the system, and we are dealing with steady flow, right? We are studying steady flow. So steady flow means there should not be any change in the energy of control volume with respect to time, right? This we know. So we can say that for a steady flow, the energy which is coming in is equal to the energy which is coming out to maintain the steady flow in the control volume. So we can write that, and also we know U1 plus PV is equal to H, enthalpy. So we can write H1 plus V1 square upon 2 plus GZ1 plus Q is equal to H2 plus V2 square by 2 plus GZ2 plus work done by the control volume. This is the energy which is coming inside is equal to, this is the energy which is coming out of the system. This is nothing but, we can say that energy is conserved, right? The energy which is coming in is equal to energy which is coming out. This is the conservation of energy for an open system. Conservation of energy for an open system. So this is your first law of thermodynamics for an open system, right? We already studied the first law of thermodynamics for a cycle, which is equal to, for a cycle we already studied that summation of heat transfer will be equal to summation of work transfer, right? This is the first law of thermodynamics for a cycle. After that we studied that dq is equal to du plus dw or de plus dw. This is first law of thermodynamics for a process in a closed system, and now this is the first law of thermodynamics for a open system, right? This is for an open system for a process. Now in this equation, just one thing you have to remember, in this equation everything is per unit mass. This is specific enthalpy, this is velocity, this is heat added to the system. Just remember this, Q is heat added to the system per unit mass, right? In question, if heat is simply given, say 100 kilojoule, you cannot write here 100 kilojoule. In this equation, this Q must be, you have to take care of the units. Every term is per unit mass, per kg, right? If in question this heat is simply given 100 kilojoule, you cannot write here simply heat, you have to divide it with mass. So this Q is heat added to the system per unit mass, and WCV is work done by the system per unit mass. So this is per unit mass, and heat added to the system positive, work done by the system positive. If in the question, if something like that, if question says heat rejected by the system, then you can take minus here, and work done on the system, then you can take minus here, right? All the sign conventions are earlier, which we used earlier also. Heat added to the system positive, work done by the system positive. So these are the positive values. If anything changes in your question, suppose heat coming out of the system or work is done on the system, then you can take minus sign here, and all the terms are per unit mass. So this is the first law of thermodynamics for an open system, or you can say this is your steady flow energy equation, which is the most important thing. This is steady flow energy equation.